5D is about compound interest, which is a little more complicated than simple interest, which I suppose is why simple interest is called that. The main difference is that with simple interest, you just compute the interest once, right? With simple interest, really all that we had was, if you want the interest, it's the principal times the rate times the time, and just make sure that the time units for the rate and the amount of elapsed time match up, right? Both in years or both in months or something like that. So either computing the interest by itself, or if you want the accrued amount, you could do it like this. And that's it, right? So really you just compute the interest once, as opposed to compound interest where you end up computing it multiple times. So there's a lot more going on. And the reason it's called compound interest is because you get interest on top of interest, more or less. Because what'll happen is that you'll have a compounding period where maybe it's every year you compute interest, or maybe every 6 months or every month or something like that. And then at the end of every compounding period, the interest is computed. So instead of computing the interest once, let's say if you were going to compute the interest every month for a year, then you end up computing the interest 12 times because you compute it at the end of every month. And the way that it works is that at the end of the first compounding period, it would look pretty similar to simple interest, where you're just computing the interest based on the principal. But then for the second compounding period, then what you compute the interest on is the principal plus whatever interest had accumulated at the end of the first compounding period. So principal plus the interest that's accumulated so far. You compute the interest on that. So what ends up happening is that what you would view as being the principal amount gets bigger and bigger and bigger and bigger, right? It's bigger for every compounding period. Like it says here, the big part is the part that's in bold plus the accumulated interest. That is the main difference. It's that which is there sort of as an effect of computing the interest repeatedly rather than just doing it once. And you do have interest computed based on interest in here, in addition to the interest based on the principal amount. But it's not like those things are separated in the computation. It's more like you combine those things together to get a new principal and then do it off of that. That's more of what it'll look like. And we'll see it the long way. And pretty quickly you'll see why you don't really want to do it the long way. Although it's good to do the long way once just to kind of get a better feel for what's going on. The long way could get really long really quick. And we're going to avoid that pothole for sure. So the other thing that we're going to need to know, so for simple interest, we have to know a few things to be able to compute the accrued amount. You need to know what the principal is, right? The initial amount invested, you need that. You need the interest rate, and you need the elapsed time. So you need those, but for compound interest, you need one other thing, which is how many compounding periods are there? So is it every year? Is it every month? Is it every 3 months? So quarterly, that's a pretty common one. What is it, right? It's got to be one of those things. So the other thing that you need to know is that how many compounding periods are there? And usually the way that's phrased is how many times would you compound the interest in the span of 1 year? Because if you know that and then your elapsed time is written in years, then your units are going to match up and you should be good to go. So that's the other thing that we're going to need. But then the most common lengths, which are down here, so annually, every 12 months, or once a year. So then your number of compoundings in a year is just 1 if it's annually. Semi-annually would be twice a year or every 6 months. Quarterly, monthly, you could have other ones, like you can have things like daily if you want it, right? Then it's 365 times a year. You can have that. You don't see it as much, but you can do it, right? Like anything that you could break a year into, you could have that compounding period if you really want it. But the most common ones are probably those. So that's mostly what we're going to stick with. All right, so how would you actually do the computation? So just for an example of what it would look like if you actually had all the individual pieces laid out. So suppose we have $10,000. So there's the P. right? There's the principal, the $10,000. Invested in an account with 6% interest. There's the R, the 6%. Compounded quarterly. So the quarterly is 4 times per year, right? So 4 times per year, right? That's what the quarterly tells us. And then what would be the value of the account after 1 year? So the 1 year, there's the T, the elapsed time. So we're only doing this for 1 year to keep the number of compoundings down so I could fit it onto one page, pretty much. So it was for pragmatic reasons. So what I figured was that this would be enough to get the idea, because we're going to have to do it 4 times. And that's also enough to see the kind of the cautionary tale of if you always do it the long way, sometimes it gets really, really long. All right, so if the interest is compounded quarterly 4 times a year, then the elapsed time for each compounding would be 1/4 of a year. Right? If you're going to write it in years, right? If you're going to write it in months, you'd say it was 3 months. But since the interest rate is written as 6% per year, then we'll write out the elapsed time for the compounding periods in years as well. So 1/4 of a year. That's going to be a better phrasing than 3 months, because then the units are going to match up. All right, so for the first compounding period, our principal is the 10,000. The rate per year that we had was the 0.06, and then the time is 1/4 or 0.25 of a year. Okay, well, you can use the old formula that we had for simple interest. It's just that you have to do it over and over and over again. You'd have to do it for every compounding period, and that's what we're going to do. So this is what the long way is. It's use the simple interest formula over and over and over and over and over. Do it for every compounding period that you have or that you need. So, all right, we can sub everything in, right? 10,000 for P, 0.06 for R, 0.25 for T. Simplify it down, you end up with 10,000 times 1.015, which is $10,150. Okay, fine. That one looks like it did before. Second compounding period, check this out. Right here, look at what the principal is now. It's what we ended up with at the end up here. Because for the second compounding period, so we're starting at the end of that first period where the compounding is done, and now we've got the 10,150. So for the second period, that's where you start. So that's the new principal amount. And then everything else is still the same, right? The compounding period is the same length. It's still 1/4 of a year, and the interest rate per year is still 6%. So the only thing that changes is we had that new principal. Okay, fine. So now it's that number times 1.015, and we get 10,302.25 cents. And then look where that shows up in the third period, because the amount at the end of the second period after the compounding is done is going to be the same amount at the beginning of the third period. So now it's the $10,302.25. We're going to multiply that by 1.015. We end up here. And then I'm going to have to scroll down a little bit, even though you can see it at the bottom of the screen right now. But that's where we're going to start the fourth compounding period. And then, okay, we're going to take that number and multiply it by the 1.015, and we're going to end up here, and this is actually the answer. Right? Because now we've gotten through a year, because we did first 3 months, then next 3 months, then next 3 months, then last 3 months, full year, broken up into 3-month intervals. And okay, we got it, right? 10,613.63. That doesn't look that bad, right? It's like, well, you just keep multiplying by 1.015 every time, right? Once you figure out what goes in the parentheses there, right, the 1 plus RT part, this doesn't look that bad. No, but that's because we only had to do it 4 times. What if, hypothetically, we were going to do this, I don't know, let's say we had monthly compounding, so we're going to do it 12 times a year, but then we're going to do it for 15 years. What about that? That's 180 compoundings. So yeah, it would be about this hard, but there would be 180 of them instead of 4 of them. That sounds like a bad idea, right? It's not hard, but that's way too long, right? Like that seems outrageous to have to go through that kind of computation, but we don't have to. There's a better way to do this. So there's a short way, and it's right there, right? So that's the thing you want to be looking at, that formula. That's how you can do compound interest all in one shot, regardless of how often you're compounding and how long your elapsed time is. So that example we just did real quick, yeah, that one's not that bad if you do it the long way, right? It's just 4 individual computations. It's not that awful. But if it was 180, that feels kind of awful, right? That's really long. I don't want to do it. I'm going to assume that's a universal sentiment that nobody else really wants to either. So we've got another way to do things where it's nice and short and compressed. Let's do that. All right, so the way that the formula for compound interest is typically written is usually just, here's what you get as the accrued amount. If you really wanted the interest, you could get it. It would be that minus the principal. So if you really wanted the interest, you could get it. It would be A minus P, right? Like if you took the difference, that would give you the interest. So I guess really it's P times 1 plus R over N to the NT minus P. That would be what the interest is. I don't think that will ever come up. I ran the homework 4 times and there was never a question that said, what's the interest? They were all either what's the accrued amount, or ones where maybe they gave you the accrued amount and you had to back solve for the principal. That's it. And usually the thing that you really want is the accrued amount anyway, rather than the interest in isolation. So, all right, let's take a look at this formula. So it looks a little bit different. Right? It's more complicated than the simple interest formula. That's why the simple interest formula is simpler, right? I guess that's why it has that name. But most of the symbols in it are things that we've had. So A is still the accrued amount, P is still the principal, R is the APR, so it's the interest rate per year, right? So with that time unit. T is the elapsed time written in years, and then N, that's the one new thing. The N is how many times you compound per year. So then if you're going to compound annually, N is 1. If you're going to compound semi-annually, then N is 2. If you're going to compound quarterly, N is 4. Monthly, N is 12. Daily, if you really wanted it, would be 365. So that's what N is. That's the only new thing. And look how short it is. Right? There's the example from the last page. So it was quarterly, so N is 4. Right? So there's our one new value that we got to sub in for with this formula. And because then if you look at where everything gets subbed in, it's like, all right, well, P is 10,000. Then R would be 0.06, or you convert the 6% into decimal form. N in the denominator would be a 4. And then in the exponent, N is 4, and then T is 1 because it was over the span of 1 year. All right, well then if you simplify, 0.06 divided by 4 is 0.015, add that to 1. I kind of did that all at once and said, okay, in the parentheses, that's 1.015. You're going to raise that to the 4th power, and then multiply by 10,000, right? Following the order of operations, you have to do the exponent first. So when you're putting that into your calculator, I guess it depends on what your calculator can do. Like if you have a graphing calculator where you can put a whole bunch of stuff in one line, then you could just type it in like that and your calculator will know how to do the order of operations. It'll do the exponent first. But if you have to go one operation at a time, then do the exponent first, the 1.015 to the 4th power, and then whatever that is, then multiply by 10,000. So what you end up with, notice this. The cents aren't the same. If I can scroll up a little to get both of them on the screen at once, there we go. We had 63 cents before. The 64 cents is better. The reason is that with the 63 cents one, if I go up there, I think if I point at it with a different color just to kind of differentiate this a little, this one is rounded off. So it's rounded to the nearest cent. But because that one's rounded, that's why the final answer is different by 1 cent. The one down here where it's using the compound interest formula, there's no rounding, right? Nothing was rounded off, so no rounding of intermediate steps. I guess that's a good way to say that. And that's what you want to do. So what I would advise, rather than like if you raised 1.015 to the fourth power and then rounded it off and then multiplied by 10,000, that's a bad idea. It's better to not round any intermediate steps and then just round off at the end if you have to, like round to the nearest cent at the very end. And the homework will stick that into the instructions where it'll say don't round off until you get to the very end. But your calculator can handle that, right? Like it'll carry out way past 2 places. And plus that way you don't write as much, right? There's also that if you don't round any intermediate steps. So just round off at the very, very end. That's the way that you want to handle that. And just for comparison's sake, check this out. With 6% simple interest, so if we had just the one computation of the interest at the end, it's not as much money. So is that a thing that always happens? Actually, yes it is. If you have compound interest, the monetary amount gets bigger. And it's because of the idea of computing interest on top of interest. Right? That's what does it. That's why you get a bigger monetary amount. So that happens here, but that will happen every single time. That what you'll get with compound interest will be a larger amount of money. All right. So I figured this wasn't the greatest example because it's a difference of $13.64. And you look at that, you go, yeah, that's bigger, but that's just a little bit bigger. Doesn't have to be. If I stretch out the amount of time, so this example from 5C, so this was the first example. It's right off the bat in the 5C notes. If you have an investment of $15,000 that pays 4.6% simple interest, and it was, what was the total value after 10 years? Well, we just subbed in, right? We just had to convert the 4.6% to decimal form. In the parentheses, that simplifies to 1.46. You multiply that by 15,000, you get 21,900, right? So we had that. But then with compound interest, let's say we're going to compound quarterly, right? Because I need something there. I need it to be like monthly or quarterly or something. I just picked quarterly. But what would be the total value of that investment after 10 years? Well, if you're compounding quarterly for 10 years, then interest is going to be computed 40 times because it's going to be 4 times a year, right? So 4 times a year, 10 years, that's 40 times. And look at what happens if you sub in. So now n is 4. So then I'm going to have 1 plus 0.046 divided by 4 raised to the 40th power. And what's in the parentheses will simplify to 1.0115. You raise that to the 40th power, you multiply by 15,000. Look at this. Look at how much bigger this is. Right? Like, that's a non-trivial difference. Right? It's, right? I mean, it's almost $1,800. I mean, right? I mean, if someone would offer me an extra $1,800, I'd be fine with that. I would gladly accept. Right? That's a lot. Just for computing the interest differently. And if it's a longer time frame, that's the kind of thing that you see. Like, you see a larger separation between what you get with simple interest and what you get with compound interest. That's what the biggest thing there is, that's over 10 years. Whereas the last one was just over 1 year and you don't see that big of a difference. But here, you get a nice sizable gap because over time, they diverge. They get farther apart. So in general, you do get a larger amount with compound interest. You get a larger accrued amount. So that's good for investing, bad for taking out loans, right? Because if you're taking out loans where the interest is going to be compound interest, that means you're paying more back later. So there it would not be great. And then the other thing is the more frequently the interest is compounded, the bigger the accrued amount gets. So like if you compound monthly, that's going to be more than if you compound quarterly. Because the more that you're compounding, the more that you're computing interest on top of interest. So check this out. This next page actually took forever for me to type, but I wanted to get this in here. I really wanted to get it in here because the typing was, yeah, it was lengthy. Even with the parts that I could copy. Admittedly, I did copy some of these parts. and then change the numbers. But still, this took an awful long time to make. So let's see. I just took the same numbers. Like if P was $15,000, same interest rate of 4.6% and compounded over 10 years. So if you did it annually, where then N would be 1, you end up with 23,518. But then look at the jump just from annually to semi-annually, right? You go from here to here, twice a year instead of once a year, you get over an extra $100 just from that. The amount of the jump will gradually decrease. Like the numbers will keep going up, but I guess the rate of change will go down. Because then if you look at this one, the quarterly one, which we already know what it is because it's on the last page, the jump isn't quite as big, right? It's a jump of like $61. So it's not as big of a jump. And the size of the jump will keep getting smaller. So if you do it bi-monthly, right, so every 2 months, then that's going to be, I mean, it's bigger, but it's not bigger by as much, right? The jump isn't as big. And I guess if you want to get into the semantics, because I guess like in normal conversation, people use bi-monthly to mean two different things, really, right? It either means once every 2 months or twice a month. Really, it's supposed to be, and I guess like in accounting, then you have to be kind of a stickler about it, right? And in finance too, where bi-monthly is supposed to be every 2 months, and then semi-monthly is supposed to be twice a month. So like semi-monthly, twice a month, like how semi-annually is twice a year. But anyway, I mean, I guess I figured that it was worth bringing that up because that word, like in its regular use, does tend to have two different meanings. Monthly, that doesn't have two different meanings, right? That's 12 times a year. Okay, well then N's 12, it gets something, a little bit bigger, but not as big of a jump. And if you want to go bigger or more frequently, you can. I figured the next one would be daily. I guess you could do weekly, right? I guess that would be a natural step in between. You could do it 52 times. But I did it for daily. And then I think I did it for like every minute. Yeah. So you could do an hourly if you wanted, like the number of hours in a year. That's not that hard to compute, right? It's just 365 times 24. And then you could do it every minute. You could do it every second. You could do it every 100th of a second, right? You could keep going if you want. But look at how small the difference is between daily and every minute. It's not even $1. So after a while, like, yeah, it keeps going up, but it doesn't really go up by that much anymore. So, I mean, you can have all these different breakdowns, but you can kind of see why if there's some interval of time, like usually you don't end up with something like really, really small. And there's actually a way to do it where your interval of time is approaching a length of 0. And we're actually going to do that one instead of ones where you end up with like really little amounts of time and giant exponents. So we'll see it in a little bit. But let's see. So we'll have a few examples first, and then we'll get to that. All right. So this one says Peter invests $42.50 in an account paying 5.1% interest compounded semi-annually. So semi-annually, that means N equals 2, right? Compounding twice a year. So how much money will he have in the account if he keeps it for 6 years? All right, so let's see what we got. Our principal is the $42.50. So I'm just going to write everything out first and then stick it all in the formula. Let's see. Then the next thing in the wording is the 5.1%. That's R. I just have to convert it into decimal form, so 0.051. Next thing is that N is 2 from the semi-annually. And then at the end, he's going to keep it for 6 years, so that's the elapsed time, so that's T. All right. So then our formula was that A is equal to P times 1 plus R over N raised to the power of NT. And we should just be able to sub everything in now. So we'll have 42.50 times 1 plus 0.051 over 2 raised to the power of 2 times 6. I do know what that is in the parentheses simplified down. So let's see, this will be 4250 out front times 1.0255 raised to the 12th power. And if you simplify that and just make your calculator do everything, don't round any intermediate steps off, what you will end up with is $5,749.33. You'll have to round that to the nearest cent, but that's what you get. All right. So then I figured I kind of wanted to have two examples like this. So the Flory one and number 2, that's the same thing as the Peter one. It's just with different numbers. So the main thing that I wanted to be different is how often the compounding happens. So when Flory invests $7,100 into an account paying 4.7% interest, the compounding is monthly. So there, N is going to be 12. Right? Monthly is 12 times a year. And then how much will she have after 9 years? Well, let's see. Well, I guess let's see what we got first of all. So P, the principal is the 7,100. Then the interest rate is 4.7%, or in decimal form, 0.047. And we know that N is 12. And then 9 years of elapsed time, so T is 9. Okay. So then the accrued amount will be principal times 1 plus R over N raised to the power of NT. So if we sub everything in, we're going to have 7,100 times 1 plus 0.047 over 12 raised to the power of 12 times 9. Oh, there's a nice big exponent. That's going to be 108. The other thing that I wanted to have happen, and I did it on purpose in this one, the thing that's in parentheses, if you try to simplify that, you're going to get a decimal that doesn't terminate. The one in number 1 does, because you're dividing by 2. Right? Dividing by 2, you get nice things. Dividing by 4, you get nice things. Dividing by 12, I mean, you'll get repeating decimals, but you won't get ones that terminate all the time. Right? Sometimes you will, sometimes you won't. This is one where you don't get one. So if we're still going to try to avoid rounding off intermediate steps, we're going to have to take an extra precaution this time. So I'm not even going to simplify this. So what I would do with this, like putting it into a calculator, I would just put in the 1 plus 0.047 over 12 first. And then just whatever that is, so like enter, have your calculator figure that out, then raise that to the power of 108, then multiply by 7,100. That's what I would do. And what you'll get here is, it's quite a bit, 10,829.44. All right, so what I would do with a calculator, I think this is actually worth me writing it out, even if it's just in shorthand over on the side. But with a calculator, first, I would do just the 1 plus 0.047 over 12. And I guess if you have a calculator where you can only do one operation at a time, then you're going to do the 0.047 over 12 first and then add 1 to it, right? To get the order of operations to work out the way it's supposed to. Then the second thing is whatever that is. So I would do that and then enter. And then I would have the previous answer. So whatever that is. So answer to the power of 108. And then enter. And then whatever that answer is, I would multiply by 7,100 and then enter, and that's what you're supposed to get. So that's, I think, the way to go. You could put this in all in one line if you've got a graphing calculator. You just have to make sure that you put the parentheses in. Right, so you'd have the 7,100 times, and then the 1 plus 0.047 over 12, in parentheses, and caret 108. You can put that all into one line. I usually go piece by piece, but that's just a personal preference thing. If you've got a graphing calculator, you could make it do the whole thing at once. Let's see, number 3 is like 1 and 2, except that instead of figuring out the accrued amount, you have to figure out the principal. Because it says what Marcia wants to have at the end. So we have the elapsed time, right? 15 years, 3.4% compounded quarterly. Okay, well then there's T, there's R, and there's N, like rapid fire, all in that first sentence. And then it says she wants to have 18,000 at the end. All right, so let's see what we know here. We know the elapsed time is 15 years. We know that the interest rate is 3.4% or 0.034 if you write it as a decimal. Compounded quarterly means that n equals 4, right? So the word quarterly has given us that. And then the other thing is we know what the accrued amount is supposed to be. At the end of the 15 years, she's supposed to have 18,000. So what we're going to have to do here is we're going to be solving for P, because it says we're solving for the initial investment, right? That's the principal. Same thing. So, all right, it's the same formula. It's just that it's not solved for P, and we'll just have to solve for it. It won't be too bad. It's a little bit different, though. So we've got that A is P times 1 plus R over N raised to the power of NT. And then if we sub in, A is 18,000. Don't know what P is yet. And then we'll have 1 plus 0.034 over 4 raised to the power of 4 times 15. All right, so then we've got that 18,000 equals P times, and the thing in parentheses is 1.0085 if you do the division, and then I guess add that value to 1. And then we're going to raise that to the 60th power. If you're going to avoid rounding intermediate steps, then I guess you would divide both sides just by this expression, the 1.0085 to the 60th power. So you would end up with, and I'm going to rewrite this with the P on the left just because I think that's easier to read, but you should get that P is 18,000 over 1.0085 to the 60th power. And what that ends up being is 10,832.24. Which doesn't look that big to get 18,000. The reason it doesn't look that big, it's because it takes 15 years, right? That's what's doing it. Long time frame. You don't need to invest as much. But how would I do that with a calculator? Just to duck around all the intermediate steps. So with a calculator, I would do the denominator first because it's got the exponent in it. So I would do the 1.0085 raised to the power of 60. And I guess you don't really even need the parentheses, right? It would just be, so I should get rid of them, right? You wouldn't put them into the calculator. They're kind of redundant. But you would do that. And then what you would do after that, I guess, is you would have 18,000 divided by the answer from the previous line. So if you're going to do it step by step, I think this is how you would do it. And that should give you the right answer. All right, let's see, 4. One more example of this kind of thing. So with 4, it's phrased as being a loan instead of an investment, but you still basically do the same stuff. So a loan's paid off in 12 years with a total of $125,000, had a 5% interest rate compounded monthly. So we have to back solve for the principal again. So this is like 3, even though it's phrased as being a loan instead of an investment. So let's see what we've got. 12 years, there's the elapsed time. And then the amount that it's paid off with, that's the accrued amount of the loan, right? So somebody borrowed money, then the interest piled up, right? It compounded. And then at the end, when they paid it off, that was the accrued amount after 12 years. So that's what the 125,000 is here. That's the A. 5% interest. All right, that's 0.05 as a decimal. Compounded monthly, that means N has to be 12. All right, same formula. P times 1 plus R over N to the NT. All right, so A is 125,000. And we're solving for P. And then we're going to have 1 plus 0.05 over 12 raised to the power of 12 times 12. Another nice big exponent, right? 144. So then, all right, we're going to get 125,000 equal to P times, and 0.05 over 12 is not a terminating decimal, so I'm still going to write this as 1 plus 0.05 over 12. And then that'll be raised to the 144th power. So we want to get the P by itself. You would divide both sides by 1 plus 0.05 over 12 raised to the 144th. And what you would get is that P is 125,000 over 1 plus 0.05 over 12 to the 144th. And what that ends up being is 68,687.02, which is a weird initial investment amount with that 02 on there. Who knows? Maybe somebody just moved all of their money from some account over, and it happened to work out to be that, and just dumped that into the loan. And then serendipitously, it worked out to be a nice round number of 125,000 when they paid it off. But so yeah, they needed that exact amount somehow. Let's say. But anyway, this is another one where I think the way that you would want your calculator to do this would be kind of like what we ended up doing with number 2. So if I go up there for a second, that was the other one where it had one of those non-terminating decimals. So that's probably the kind of thing that you'd want to do here. So I'll write this one out with the calculator too. So what I would do, denominator first. So I would do what's in the parentheses. So the 1 plus 0.05 over 12. And again, if you don't have a calculator that can do multiple operations at once, you have to do the division first and then add a 1. Then after I did that, I would raise that number to the 144th power. Then you've got your denominator, and then you just have to divide 125,000 by that number. So it would be 125,000 divided by answer. All right, so 4 is basically number 3, except with a different context. And I guess with different numbers, right? But it's a loan instead of an investment, but they work the exact same way, right? It's still continuously compounded interest, so same sort of process to figure out what the principal would have to be. All right, so before, and I guess I can kind of scroll back up to point at it, we had this idea, and here it is on this page, like toward the bottom. You can break down a year into nice little tiny increments of time if you really want to. You could do every minute, you could do every second, you could do every millisecond if you really felt like it. But at some point, it's kind of not worth it to keep, breaking down the year into like these fine little tiny intervals. So it's always possible to do that, to make the length of a compounding period shorter. And then I kind of put it in parentheses where they just keep getting shorter and shorter and shorter, right? Every day, every month, every day, every hour, every minute, second, hundredth of a second. You could keep going if you really wanted to. But if you're breaking down the intervals of time, then the number of compounding periods is going up, right? 12, 365. 365 times 24. 365 times 24 times 60. 365 times 24 times 60 times 60. And then whatever that is times 100, right? You're getting some big numbers here. And you can always keep going. But is that worth it? Well, actually, no, because we have this concept that shows up next, which has to do with E. And this is why E shows up in the last section. So toward the end where there are those exponential functions, E shows up in there. E is very useful, actually. And it's very useful in finance because continuously compounded interest, which is the thing that we're talking about, it runs on the concept of E. So we defined E as what this expression right here would approach as n increases. And I think when we went through it, it was like if you put in like 100,000, then you get the value of E that your calculator has to like the first 5 or 6 places. So you don't really need numbers that are too huge to get a good approximation of E. But as n gets bigger and bigger and bigger, that thing that's circled in maroon right now will approach E. So as a consequence, 1 plus r over n to the nt. So that's a little bit more complex of an expression. It's got an r in that numerator where there used to be a 1, and now we have an n times t instead of just an n. But that will approach e to the rt as n increases. Oh no, I'm missing an e. So this approaches e. How did I miss that? I gotta fix that before I post it. All right. So then the formula ends up looking really simple because then, well, what's the difference between this first indented bullet point and the one underneath? Just multiplying by p. But then that's our formula, right? So we'd have that a equals that, right? That's what we had so far. But now we're going to end up with a equals p e to the rt for continuously compounded interest. So conceptually, this is more difficult because it involves E, but algebraically, it's actually going to be way easier. So that's nice. That's a nice side effect to have. And then as far as, let's see, and just to have a different color, I guess, I'll just do this in blue. So the thing that I'm pointing at now, the blue arrow, that line, like there is a justification for it. You would do it if you take calculus, you'll see it. And all of this stuff uses the concept of limits, which is a big thing in Calc 1. And I tried to write this up where I didn't say limit ever. But that's where you would see like the justification for that. And actually, maybe. The justification for that particular thing might actually be in Calc 2. Because in Calc 2, that's where you do exponential growth and decay. And this is growth, right? Like the amount of money gets bigger. So it might actually fit in there. That's actually more likely now that I'm thinking about it. It's probably toward the beginning of Calc 2, where you would actually go through the justification of how that limit works itself out. But continuously compounded interest, it's the idea of like, well, what if we took this to its logical extreme and said we were going to compound the interest infinitely many times every year? And we say, well, you couldn't do that by hand, right? You'd never finish. That's true. But you can make a computer do it. You can make a calculator do it. So it's not one where you could do it by hand and do every single period because you'd never get done. Also, because if you had infinitely many, like how do you sub in an infinity and simplify it down? That doesn't make sense either. And basically you have the idea that if the number of compoundings is approaching infinity, then the length of the compounding period is approaching 0. Right? So like you get into these abstract things a little bit where if you try to do it by hand, it doesn't really work. But since we have the idea of that number E, we can do this. So it isn't one where you could go period by period computing it by hand, but this is actually a thing in finance that's relatively common, to have continuously compounded interest. So notice you don't need n because, well, I mean, what would n even be? Right? Like, how do you sub in an infinity? You don't. So it's just p times e to the rt. So the algebra is actually easier. Nothing wrong with that. So that's what we're going to see in these examples. So where it says Rocky invests $32.50 into an account which compounds interest continuously, right? So there's the E, right? When you see the continuously, you go, oh, I need the E, right? If you just remember that, I think you're going to end up in the right place. Continuously means E. At a rate of 2.9%, and then how much will Rocky have after 4 years? Well, let's see. So the principal is the $32.50. Then R is 0.029. And then it's 4 years of elapsed time. And we should be able to do it from there, right? Because A is P times e to the RT. So if we sub in, let's see, we've got 3250 times e raised to the power of 0.029 times 4, which should be 0.116. Yeah, because 29 times 4 is 116. So, okay, A is 3250 times e raised to the power of 0.116. And what you should get here is 3649.74. All right. So with this one, if you're going to put it into your calculator, presumably you have an E button, or if you have a TI, it's probably a secondary function. You've probably got a natural log key, but then if you hit the second key and then the natural log key, it'll give you E raised to a power. And if you're going to do these as separate operations, you would do that first. Although if you have a graphing calculator, you could just do 3250 times E caret 0.116. You can do it all at once. But if you were going to do them as separate operations, then you would have to do the power first, right? So you'd have E caret 0.116, and then enter, and then you would have 3250 times the previous answer, and enter, and then you've got it. So if you're going to do it in separate lines, that's what it looks like. Or if you have to do it in separate lines, that's what it looks like. All right. The only other thing that might happen with the continuously compounded interest is what if you have to back solve for the principal? And that's what number 6 is. So with EVA's investment here, we've got the elapsed time, we've got the interest rate, we've got compounded continuously, there's the E, and then we have the accrued amount of $97.62. And we've got to figure out her initial deposit, aka principal. All right, so let's see what we got here for EVA. We've got the elapsed time of 11 years, we got the interest rate of 0.042, and we've got the accrued amount of $97.62. All right, well, we know what our formula is. A equals P times e to the RT. And we know A is 97.62. Solving for P. And then E raised to the power of 0.042 times 11. 0.042 times 11, let's see, 420 and 42 is 462. So 97.62 equals P times e to the 0.462. And once again, if we want to duck rounding intermediate steps, then to get P by itself, you would divide both sides by e to the power of 0.462. And you'd get that P equals 97.62 over e to the 0.462. And then you can do it from there, and what you should get is, let's see, it's 61.50 28, but we're supposed to round to the nearest dollar. So rounding that to the nearest dollar, we have to round this one down. It would be 61.50. All right. Oh, another thing, if you want to get fancy and start using like laws of exponents, 9762 divided by e to the 0.462. Instead of dividing by that, you could rephrase that as multiplication if you use a negative exponent. So if you want to do it like that, you could. You don't have to. I figure the way I wrote it here would be the way that probably felt the most natural. It's the one that feels the most natural to me. So I kind of went with my own intuition there. But if you wanted to use a negative exponent, you could. But what I would do with that is I would get the denominator first. So e to the 0.462. And then I would take 9762 and divide that by the answer on the previous line. And then that's it. And I guess since I said it, I'll put this in a different color. If you really want to use the law of exponents, you could. And if you wanted to write this as 9762 e to the negative 0.462, that's correct. You don't need to know that that works, or because I don't think that makes things any easier. Like you still have to put it into a calculator anyway. And I prefer to not have negative exponents myself. Like I would rather divide than have a negative exponent. Right? I mean, like that's kind of what it comes down to, right? It's one of those two things. I would rather divide, but if you would rather multiply with a negative exponent, it'll work fine. So since I brought it up, that's, I guess, what it would look like. All right, then the last thing in this section is the idea of effective annual yield. Really all that is, it's the amount of interest that you get in the first year converted into a rate. So divided by the principal. So really what this is, and let me keep it brown. I want a different color that sticks out. So really what this is it's the interest in 1 year divided by the principal. However, the way that the formula is set up, it's not set up to just give you the interest directly. So what you end up doing in order to get the numerator is that you get the accrued amount after 1 year and then subtract the principal off, because then you'll be left with the interest. And that's basically what you do. And then you just divide by the principal and you've got it. So what's this for? If you are, I guess, if you're trying to pick out between different investments, or if you're trying to pick out between different loans, and the way that they're listed is like they have different compounding periods, or then if you're just trying to eyeball them, it would be harder to figure out which one was to your advantage, right? Because they're probably going to be close to each other. And then like eyeball them, you're like, oh, well, I can tell that this number is almost the same as this number, right? That's kind of where you end up. So then that's where this comes in handy. Because then it's a quick computation, relatively, and then you could be like, aha, this rate is going to give me a little bit more money than this one on this investment, so I should go this way, right? That's what it's for. And this is what it is right here, so this formula is going to be the thing that we're mostly concerned with. And then the thing at the bottom, the annual percentage yield, it's the effective annual yield just converted into percent form, so just multiplied by 100. That's all it is. And I think in the homework, they ask for annual effective rate instead of annual percentage yield, even though in the notes it says annual percentage yield. So that's why I said either this or this. I mean, those terms are synonymous. But I think the homework usually says annual effective rate, because when I ran it over and over and over again, I kept seeing it over and over and over again. So I would assume that that's what it's going to do when you do the homework. All right, so let's see. We've got a couple examples here. And then number 9 is kind of wild, which also means not necessarily short. But we'll get there when we get there. On the other hand, number 7 is really short. That's why the amount of room for number 7 is so small. But we have that Carlos invested 2,500 at the beginning of the year, and at the end of the year he had 2681.57. Why is number 7 so short? We already have the accrued amount after 1 year, right? Because here's the principal. Here's the accrued amount after 1 year, which, if I go up for a second, I wrote the formula, so where it's circled with an a sub 1. That sub 1 just means after 1 year. I wrote it with parentheses like a of 1, like with function notation initially, but it looked too much like multiplying, so I figured the subscript might be a better way to go. But that's all that's supposed to mean. It's the accrued amount after 1 year. And then we want the annual effective yield. Okay, well, if we know what P and A1 are, then this is not long. So we know P is 2,500, and we know that A is 2681.57. And then if R sub EFF, our effective interest rate, is going to be, let's see, so it's going to be A1 minus P over P. So it's going to be 2681.57 minus 2,500. And then that amount is divided by 2,500. So that difference in the numerator is 181.57. So this is 181.57 over 2,500. And what you end up with, at least rounding off, is about 0.726. And we're supposed to get this as a percentage rounded to 2 decimal places. That's why I rounded to 4 places here when it was in decimal form, because then when you convert it into percent form, you move it over 2 places, and we're good to go. 7.26%. All right, so number 7's nice and short. Yeah, that's because a sub 1's already done. Usually it's not. So number 8 is like number 7, except that you also have to get a sub 1 on the way there. And that's usually what they're like. So number 8, we've got that Anne invests her money in an account paying 6.1% interest compounded semi-annually, so twice a year. And then what's the effective annual yield? All right, let's see what we got to do here. Oh, another thing. Where's the principal? It's not here. That's actually okay. You'll see why when we do the computation. It's not obvious right now, probably, and that's fine, but you'll see it. Because there's a point where we can cancel out the unknown principal. And I think once it's there, it'll make sense. So let's see. Our interest rate is 0.061. And we know that N is 2, right, semi-annually. And I guess T is 1 when we use the formula, right, because it's accrued amount after 1 year. So we're going to use the formula that we're using toward the beginning, right? If it's compounded semi-annually, that's not continuous. So we're going back to the old standby here, where A is P times 1 plus R over N to the NT. And this is A sub 1, right? Well, I guess here it's just A, and then A sub 1 will be when T is 1. That makes more sense. So A sub 1, that's going to be P times 1 plus 0.061 over 2 raised to the power of 2 times 1. Okay. So then A sub 1 is going to be P times 1.0305 squared. And for now, I'm just going to stop here. So then what we want is the effective annual yield, right? The R sub EFF. And we said that was going to be A sub 1 minus P over P, right? But A sub 1, we have an expression for it, right? It's not simplified all the way because we don't know what P is, but watch what happens if I put this in. I'm going to get P times 1.0305 squared minus P over P. All right. The numerator has a common factor because P is a factor of both terms, right? You got the two terms, like one's being subtracted from the other. So you could factor a P out of the numerator. This is the key maneuver here when you don't know what the principal is. It's doing this. So if I factor out P in the numerator, I'm going to be left with, I need an extra set of grouping symbols to get this to look right. That's why I've got the bracket here, but I'll have 1.0305 squared minus 1 with the P factored out. And then this is over P, right? Those P's are going to cancel or divide out, however you want to look at that. And what you're going to end up with, so, you know, let me cancel them, but in a different color. There. Out. Right? You can cancel them because P isn't going to be 0, right? So you don't have to worry about the division by 0 or anything. So yeah, it's just some number. You can cancel it out. Some unknown number, but it is just some number. So, all right, then our effective annual yield is going to be 1.0. Pen stopped working for a second. 1.0305 squared minus 1. And if you put that into your calculator, it ends up being about 0.0619, or converted into percent form, about 6.19%. All right, so we made something out of this, where at first it looked like that might be tough since there was no principal amount to work with. But as it turns out, we had a maneuver to get around that. So this sort of thing does show up in the homework. It showed up every single time. What happens in number 9 did not show up every single time. It happened the first time I ran it, and then it never showed up again. But I thought, like, this was the most intense thing that I saw, like the most intense type of problem. And I thought, I better throw one of these in. Because these are, like, it's a step up from the other ones, I think. Because it involves, like, roots, which we haven't really had to deal with. So, all right. So what interest rate, compounded semi-annually, gives you an annual effective rate of 9%? So now we're not solving this directly. We're back solving for R. All right. Well, let's see what we got. We know compounded semi-annually. We know what that is. Right? N is 2. And then the annual effective rate of 9%, convert that back into a decimal, that's 0.09. That's all we have, right? That's it, right? Like we went through the whole sentence. That's it. All right. But in order to get the effective yield, then we must be able to write out the accrued amount after 1 year somehow, right? Even if it's just in terms of P, like it was with the last one, there must be a way to get an expression for that, right? So, okay, let's see what we can do. So we know what we have generally, that we have this. But then if we want a sub 1, that's when T is 1, right? So we just got to remember that. So we don't know what P is yet. We also don't know what R is yet, because that's the thing we're trying to solve for. But N is 2, and then this would be raised to the power of 2 times 1, right? Since a sub 1 is the accrued amount after 1 year. All right. I guess I could clean up that exponent slightly and say that that'll be 1 plus R over 2 quantity squared. All right. But then what we know so far, because I think that's about as far as we can take this, that the effective annual yield, this is going to be a sub 1 minus P over P. And if we sub in for a sub 1, and we can sub in here, because we know what the effective annual yield is, it's 0.09. So we can say, well, then 0.09 must be equal to P times 1 plus R over 2 quantity squared minus P all over P. Oh, hey, look, we're kind of in the same position we were in last time, where we're going to be able to factor a P out of the numerator and then cancel it. And that's exactly what we are going to do with this. So, let's see, I guess it might be better if I just go up toward the top. Just start it off up here. So 0.09 would be, in the numerator, we can factor out the P. Then we're going to have 1 plus R over 2 quantity squared minus 1 after the P is factored out, and then a P in the denominator. Again, we can cancel those. So I guess red means cancellation. At least the number 8, so we can do it again here. All right, so we cancel those P's. What are we left with? Well, we'd have that 0.09 is equal to 1 plus R over 2 quantity squared minus 1. And we got to solve that for R. Okay. The thing that has the R in it is that quantity getting squared. So let's just get the thing that's being squared by itself. So if you add 1 to both sides, what we're going to have is that 1.09 equals 1 plus R over 2 quantity squared. If you take the square root of both sides, that's what you got to do next. So if you do that, you'd have the square root of 1.09 would be equal to the square root of 1 plus R over 2 squared. But if you take the square root of a square, you just get 1 plus R over 2. And then over here, you got the square root of 1.09, whatever that is. So, yeah, I guess here to here, it's the square root of both sides. But now we can do it, right? Now you can look at it and you go, all right, I get it. I see how you would solve for R from here. You get the term with the R in it by itself. So like you subtract 1 from both sides, and you'd get that the square root of 1.09, whatever that is, minus 1 is equal to R over 2. And if you want R by itself, you got to multiply both sides by 2. So then, because I'm kind of out of room, I got to move up here. So 2 times the square root of 1.09 minus 1 is equal, well, it's equal to R, right? Because it's going to be equal to 2 times R over 2, but that's just R, right? So R is going to be 2 times square root of 1.09 minus 1. And then roughly, if you put the, I guess, square root of 1.09, then minus 1, then multiply by 2 into your calculator, you'll get roughly that R is 0.0881. So then 8.81%, if you want it in percent form, rounded to 2 places. All right, so a little bit different and a little bit longer. The thing that would make it even crazier is if the compounding was different. Well, I guess if it was annually, that would actually be easier. But if it was anything more often than semi-annually, it gets tougher because your calculator probably has a square root key. It probably doesn't have a 4th root key. That would be crazy. I've never seen one that did. Or like a 12th root, right? Because where that root comes from, it's to counteract that squaring, and we're squaring basically because of the semi-annual compounding. So if it was monthly, then you'd have a 12 and you have to take the 12th root. That's actually why I kept running the homework over and over, because I was like, it's doable when it's a square root, even though this is longer and a little more intense. But when it's some weird root, then depending on what kind of calculator you have to kind of know your way around the calculator a little bit to know what to do. Or you might have to convert the root into a fractional exponent. Right? Like if you're taking the square root, that's the same thing as raising to the power of 1/2. And if you have a TI, like in the 80s range, like a graphing calculator, that's the easiest way to get other roots. So like if you did have to get a 12th root, then you would just raise whatever's under the radical to the power of 1/12, and that's how you would do it. I don't think that will come up. This might, since I did see it. But I think if this one comes up, you'll just get the semi-annual one. If you get something like this, where you're being given the effective annual interest rate, and then you have to back solve for R, then, and it's not semi-annual, if it's like quarterly or monthly or something, and you can't figure it out in your calculator, then email me about it and we'll see what we can do. I'll probably have an idea of a way to get it to work, even if you don't have like a customizable root button, which actually I don't think most people will. But hopefully it just doesn't happen, that if you get something like this, it'll just be a square root, which you will have if it's semi-annual. But that, I think, would cover 5D. So 5D is kind of a big one, but there's a lot that goes on with compound interest, right? Because you got to talk about the continuous compounding. That is a thing that's in real life, and it's in the homework. And yeah, this one's kind of stretched out, but and a lot of it's about knowing your way around the calculator, because like you got to use a calculator for some of these, right? Like I guess you wouldn't have to, but if you did it by hand, like it's so long in some of these cases that it's really not going to be worth it. So a lot of this section, once you start getting the hang of it, a lot of it's really just knowing how to do things with your calculator, with whatever kind of calculator you've got. And this is admittedly a situation where if you're relying on like the Windows calculator, that can do it, but there you've got to go like one brick at a time to build the wall, basically, right? Where it's just one operation, then another, right? Rather than being able to do a bunch at once. So that I think would do it. But if you have any questions about this sort of stuff with the compound interest, certainly email me.